Hi, everyone. I'm Colleen Bertonti. I'm a computational scientist at ANL, and this talk is going to be about compiling and running for HPC applications. So Marta discussed a little bit of this yesterday, so this is more detailed and a little more extended session of some of the compilers and libraries that she mentioned yesterday. The goal of this is to give an overview of like the basic tools to allow you to take advantage of all of the resources on Aurora. So it will include talking about the different programming models you can use, and some like quick start overviews about affinity. So making sure you can bind as you want to the different CPUs and GPUs, and then linking in some of the optimized vendor libraries. I'll cover the first part of the talk, then Thomas Applencourt, Brian Homerting, Chris Rowe, and Nathan Nichols, who's filling in for Abhishek, will cover part of it as well. So we'll be switching back and forth between each of our talks. So here's just a quick overview. I'll do a reminder overview of Aurora. Some of it you heard from Marta yesterday, but just trying to pull out some key points for this talk. And also about the programming model landscape. Then we'll have short 15-minute-ish overviews and quick starts for OpenMP offload, which I'll cover, SYCL, which Thomas will, Cocos, which Brian will, Akka, which Chris will, and then another 15, and then at that point we'll pause for questions. So feel free to put questions in the chat as we're going through this, and we'll have a pause after the program model section for questions. If you have like maybe one question, we can do it in between the different programming models, but just for the sake of time, we'll try to put them all kind of at the break after the programming models. Then another 15 to 20-minute section about GPU and CPU binding with Nathan filling in for Abby, and then a section about using math and other libraries on Aurora, which we'll come back and I'll do that. Okay, so just covering references first here. This is like the main, a lot of this content is on the ALCF documentation page, which is here, as well as the Getting Started guide. I know, yeah, Marta mentioned this yesterday, but they're really good resources, so you can always refer back to them. And we'll try to point out links when possible. Okay, so first, just to give a quick motivation and some background for this talk. So again, yeah, workshop is focused on using Aurora well. I think a lot of people want to do that. So from the specification shown here, like Marta mentioned, Aurora is a very powerful system with over 60,000 GPUs and 20,000 CPUs. And then of course, the question we always have as developers is how to take advantage of these resources that are available. This is where program models come in. They're the way we target the resources we want to use. Affinity and linking will let us use the resources we want to, and then making sure we can use vendor optimized libraries is, yeah, part of the goal of this talk. So the other point from this is most of the computational power, like the exaflops and the memory bandwidth, is coming from the GPUs. So we want to focus on programming models that target the GPUs. But it is a heterogeneous system, so the CPU and the GPU side. So when we're thinking about how to structure the code and how we want to run, we need to keep in mind we have both CPUs and GPUs and that they're developed for different purposes. And also I really wanted to put this here because it helps to shed some light when we see the different GPU program models, like why they're structured the way they are, is keeping in mind the differences between CPUs and GPUs. So a CPU is designed to, sorry, a CPU is designed to reduce latency and run a single thread or a few threads very fast. So they usually run at a high frequency, and they have hardware dedicated to decreasing latency, like branch prediction and out-of-order instructions. But on the other hand, GPUs are really optimized for throughput, so optimized not for how fast a single instruction can execute, but how many instructions can be executed in a given time. So it's like the CPU is a fast sports car versus the GPU is like a bus. So again, keeping in mind the differences is helpful in how you want to structure your code, which parts would be better with a lot of like a serial, very fast branch prediction versus parallelization. So with sort of a high level hardware background, I wanted to talk about the style of programming. So again, heterogeneous, your code has to start running on the CPU. It won't start running on the GPU. So it's up to you as the programmer to use the programming language and model to tell the CPU when to offload part of your code to the GPU. So you start in the CPU, and then as the developer, You generally want to put the part on the CPU that's latency sensitive or has a lot of branch prediction or has to be run in serial. And then have the part of your code that parallelizes well run on the GPU. But of course, one thing to keep in mind is that data transfer between the CPU and GPU is relatively slow. It's orders of magnitude typically slower to transfer data from CPU and the GPU and vice versa than it is to just touch data from the CPU on the memory on the CPU or data on the GPU for the memory on the GPU. So usually best to keep the data on the CPU if you need it or the GPU if you need it and to minimize data transfers. Okay, so with that high-level background, now we'll talk about the program model landscape on Aurora. So that's listed here with the different programming models and which base language they're available in, and also some comments about whether they're vendor supported or not. Usually these are ones that you run just on a GPU or a single node programming models, and then they're combined with MPI typically to go across nodes. So first is the pragma-based programming models. So on Aurora, the ones available are OpenMP, so either just without target, so on CPUs, or with target for GPUs. So these are usually really easy to get started with. They usually involve just adding a pragma, as in the name, but sometimes you don't have as much fine-grained control of the hardware as you do with other models. However, they're generally really portable. You can write OpenMP offload code on NVIDIA hardware and then run it on AMD or Intel GPUs. And also just to note, this is the only one that has native Fortran support. So if you have Fortran, it's usually a good option. Then there are the C and C++ frameworks like Cocos, Raja, OpenCL, HIP, and SYCL. These provide a lot of control and are portable to different GPU hardware also. Usually they're not gender supported, although the genders may help provide some support. SYCL is developed by the Kronos group, which is the same as OpenCL, and it does have a lot of development from Intel, though, including they have like their own extensions too. So there is a little bit of a community supported and vendor supported can be a little murky. One other model I wanted to call it was HIP. This is the AMD's main programming model, but we have an experimental port of HIP that will run the HIP APIs and HIP kernels on top of Intel GPUs called HipStar, and that's available on Aurora as well. Then, of course, there are the AI frameworks, which if those are the ones you're interested in, then please go to the breakout room because I think this is the last time I will mention them. And the whole other breakout room is about the AI frameworks. Okay, so just to give a sense of what programming models people on Aurora are using, this is a chart of the programming models that the year one Aurora projects and the ECP projects from ECP time used. So we see a lot of different models used, OpenMP, SYCL, Cocos, Raja, OpenCL. However, from the top programming models that aren't AI frameworks are OpenMP, SYCL, Cocos, and Akka. So that is why we will next have 15-minute overview quick starts of each of those, because those are the main ones, or the top four that people are using based on surveys. So I'll go first with some overview of OpenMP, then Thomas will talk about SYCL, Brian with Cocos, and Chris with Akka. Okay, so OpenMP, I think most people here are probably already familiar with OpenMP on CPUs. So I'm just going to do kind of a quick recap and then a little bit more about running on the GPU with OpenMP. So first, why would you use OpenMP? So OpenMP is an open standard for parallel programming. It's basically an API and a set of environment variables that a lot of different vendors have implementations of. The standard document itself is really large. I mean, if you've ever looked at it, it's very large. A main reason that it's really, really large is that it's really broad and expressive. It can express parallelism to target CPUs, CPU threads, GPUs, and also vendor or SIMD units. The vendors behind all of or most of the supercomputers, for example, Perlmutter, Frontier, Aurora, NERSC, Oak Ridge, and Argonne, all have OpenMP compilers runtimes. And OpenMP is supported for the GPUs on the system. So if you want to be portable, it's a really good option. And just for quick reasons for why someone would prefer to use OpenMP over like CUDA or the C++, C or C++ frameworks is that it's really easy to get started with. It's trivial to parallelize loops. It also has some convenience directives, like for instance, the reduction clause, which lets reductions of variables be computed really easily on the developer side. So diving right in, so coming from like a CPU background, let's say you already in the past have gone through and done a lot of work to parallelize your code with OpenMP for CPUs. So you found areas that were parallelizable. And for example, in this case, just did OMP parallel for or parallel do to spawn threads in the parallel region and distribute iterations of the loop with for. But of course now, like Aurora, most systems are using GPUs. So the really nice thing with OpenMP is that since you already did all the work to parallelize with CPU OpenMP, you can, at least as a starting point, use that to running on GPUs with OpenMP offload. So if you already know the regions you want to parallelize, all you have to do is, not all you have to do is, but at a base level, what you have to do is just, you know the regions you want to parallelize, you change parallel for to target teams distribute parallel for, like shown here, and then it will target and run on the GPUs. But of course, maybe the question is, what is the meaning of these additional directives that are different from running on the GPU versus CPU? So just I'll try to go through each of the different directives so you know what they mean. So you're just going through the clauses. It also tells us about the thread hierarchy and where the different threads are running on the GPU. So the target construct is the construct that says just to take any code that's inside the offload region and run it on the GPU with a single thread. So typically your code is running along on the CPU because that's where it starts. It hits a pragma OMP target, and then it will wait on the CPU while execution control goes over to GPU and runs with a single thread in serial. But like we talked about before, we really don't want to be running in serial on the GPU unless we absolutely have to, because yeah, frequency is usually lower on the GPU and it's expensive to do data transfers. So if you want to run more threads, the teams construct creates a league of teams. Each team typically runs on a sub-block of the GPU, and in that block, usually there's some shared resource like a shared memory or shared reduction hardware. It a little bit depends on which vendor you're using where that runs, but typically like on NVIDIA, it will run on an SM. So it will target that, and then to add in more parallelism and have multiple threads within each block, which can synchronize and have barriers with each other. The parallel construct creates threads within the teams, and those will run concurrently. So you have like the coarse-grained and the fine-grained parallelism. So if you put that all back together and look at the example, we have target teams parallel, which create the thread teams on the device, and distribute for, which distributes the work. And then the last key point about OpenMP is data transfer. This is, again, really important to know when you're doing data transfer or not, because it's much slower to access memory across the PCIe from CPU to GPU, rather than directly on the memory of that piece of hardware. And it can sometimes be tricky with OpenMP, so because it does some implicit data transfer sometimes. So I wanted to go through the example. So here we have pragma OMP target teams parallel 4, which switches from running on a CPU, and then we do this DAXB on a GPU, and we need to transfer arrays A and B from the CPU to the GPU, so you do that with the map clause in OpenMP. So you list just the arrays, and you say map 2 says map from the CPU to the GPU, and from says once you're done, map from the CPU, or from the GPU back to the CPU. So to from says map to the GPU and then back from the GPU. These are the A and B are both shared and accessible by all threads of the GPU, but we also have some implicit rules for like scalars. So num and scalar are scalars that are inside the target region. By default, these are mapped as first private, so they just, each thread has a private copy and they're set to whatever they were on the host. And then loop variables like J are just per thread. Also, yeah, private per thread. Okay, so that was just a high-level quick overview There's a little more detail on the Aurora docs as well. And this is just a reference slide with the compilers and flags to use. So for Fortran C, C++, on Aurora, we're typically using the MPI wrappers. So MPI Fort, MPI CC, MPI CXX, which has the Intel compilers of IFX, ICX, ICPX. These are in the default environment on Aurora. So if you try these, they'll already be there. The flags support CPU threads as well as to run on the GPU are the same for C, Fortran, C++, so that's nice. One comment is that by default, these flags or the GPU flags are JIT. They'll do JIT compilation. So that means at compile time, you only compile the offload regions to an IR, and then at runtime, you'll have the first time you hit a target region, it will take the IR and compile it to binary. So you'll have maybe a little bit of a performance hit at runtime, but a faster compilation time. If you want to do the opposite and get binary at compile time, you can use AOT compilation. So it's just a little bit of a longer OpenMP offload target flag. So instead of Spear 64, Spear 64 gen, and then you specify what backend, which is PVC in our case. And that's also discussed on the documentation page. And then just some good news about the state of OpenMP offload implementation. So I don't want to go into too much detail, but there are a couple of OpenMP conformance benchmarks, OVO and OMPVV, which are sort of looking at how well, or different pieces of the OpenMP standard and how well different implementations are implementing them. So some of the tests are for really uncommon OpenMP directives. So you would always expect 100% pass rate at the moment. But overall, the thing I wanted to point out was this is comparing running for C++ on Polaris and Aurora, for Fortran on Polaris and Aurora. And basically sometimes it's lower because maybe they don't implement one thing and that makes a lot of tests fail. But overall, if you are running okay on Polaris with OpenMP offload, you should be able to still do a decent job on Aurora because the pass rates are all similar or Aurora is higher generally. So it's nice that generally implementations on both NVIDIA and Intel are working well. So you should be able to if you're running on one GPU, should be able to run okay on the other GPU. Then just one quick note, because I know some people have used OpenACC before, so this is a pragma-based model that isn't supported on Intel GPUs. A lot of the concepts are the same as with OpenMP offload, so you can usually porting to OpenMP offload is a good option. Intel does have a migration tool. I haven't tested this myself, but if you're interested in using it, the GitHub is here and we can take a look at it. Let me know and we can see if we can get it installed in a world readable spot on Aurora, but obviously you can grab it and test it out yourself too. So just a quick start, I put an example in GPU hack OpenMP. It's just a really simple hello world with OpenMP. So you can copy it out of the OpenMP folder, just compile it with MPI CXX. There's also a Fortran example, MPI CXX, FI OpenMP, F OpenMP targets equals Spear V, and the test name. And it should give you number devices 6 and hello world from an accelerator. And that's all I have for OpenMP.